Excellent. Okay, potential energy. Back from chemistry. What's potential energy? Phones away, please. Notes out, phones away. Laptops out. What do your laptops do now? Put them away. You have a sheet in front of you, put it in your bag, put your bag on the floor, so it's off your desk, and you have a nice clean desk. Laptops away. Birdie, laptop away. Don't need it. Things away. Excellent. What's potential energy from way back in chemistry? Where do we contain the energy in chemistry? In the molecules, where's the energy? It's in the electrons. So, chemistry, it's in the bonds. It's in the electrons. And it gets converted to things when we change the bonds around. We get an exothermic reaction. We blow things up. They get kinetic energy. Kinetic energy is not potential energy. Potential energy is energy of place. So it is energy that you can turn into other things. It is energy of stress. Let's go heavy in here. This is always a reasonable. Everybody instinctively knows this. So it stole my last defense.
No, I don't.
That's a good demonstration of potential energy, and then you turn it into kinetic energy. So, demonstrate. That's not potential energy. That's just hitting people. Although the potential energy in that case is in your muscles. In the if I just take this and I can turn it into potential energy, and then you'll cower in fear. Cower in fear. It's not cowering in fear. No cowering in fear. Or you don't cower in fear for that. Sure. That's potential because I'm increasing the elasticity. Increasing the elasticity. I'm using the elasticity.
Whoa.
And now you know this has a lot of potential. I can let it go and convert it to kinetic by zipping around the room. Or I can just press down and then release all that kinetic energy into a bang. Hold it, where did it go? Okay, so stress. Potential. Ready? Potential means must be converted. Ready? To do work. Work is an actual thing in physics. It's a description of when you take an object and you can move it. You're doing work. So if I do this, I have done some work that required some energy, that required some force. Potential energy is not currently doing work, but it has to be converted into a form in which it could do work. Converted, transformed. That's a good definition too. It is the ability to create other forms. Other than we've got potential chemical energy, and we've got potential energy of position. So I'm going to go back here. I talked about it's in the bonds. It hasn't done anything yet, so that's potential energy. I showed you elasticity, turned it into kinetic energy. But the easiest way to make potential energy on this planet is to just hold something in the air, because at this moment it has potential energy. If I let go of it, it falls down, and then it converts it into kinetic energy. So, on Earth, energy of height. What are you doing? I heard smacking. No, wasn't it? Was it Zane or maybe? Yeah. Okay. Watching. So we're going to draw the conversion. A stretched bow containing potential energy that is released. I'm so bad at drawing, but here is our bow. We've got a straight, let's put the arrow in there first. I won't draw someone holding it because that would probably exceed my capabilities. Let's say that is holding 100. J, what does J stand for? Joules. Excellent. Joules are the unit of energy. So this is all potential energy. We release the bow. Group together. Draw it on the other side. Clone.
You should copy and then paste.
There's a clone button there.
Oh yeah, it's at the top. Like the middle top.
Yeah.
Ooh. Clone. There we go. Now I can make everything back to normal. Group. Ungroup. Then I can take the arrow. Let's turn it like that. That needs to be no, you're useless. Put that away. We'll draw a new one. Now, what forms of energy was that converted into? The kinetic energy. How many joules? No.
Oh, 50.
90.
Whoa, 50, 90? 50 would be amazingly low, I think. But we've got, sure, 90 kilojoules.
Yeah.
So, kinetic, how fast is it moving? Give me a speed. 200. 200 kilometers per hour. Miles. So, like, more than 400 kilometers per hour. That's amazing. Yeah, I think we're going to need more kilojoules, but anyway.
Yeah, it's probably what, 5, 6 kilometers.
Excellent. So, 200 miles an hour? How fast is the fastest pitcher in baseball?
You can get up to about like 104 kilometers.
Isn't it like one?
No, what'd you say? 90
90 kph.
kilometers per 90? Yeah, that seems then amazingly. But an arrow. Okay. Where's the other 10 joules?
In the bow and heat.
Where's the heat?
Well, it's going to be in the arrow, the back of the arrow as well as.
So there's going to be like.
One of the thingy 75 is going 200.
No, probably not. It's cutting through. It's going to be fine. So when the bow went across this, when the bow slid across, when the arrow, so the arrow goes like this, what would that have created on the bow and the arrow? Friction, which would create heat. So we lost some energy as heat. Maybe I should do that in red.
Someone's going to
Heat. There'll be a little bit of heat. Let's say 1 kilojoule. 1 kilojoule's lost there. What else is there? Yes.
So we turn joules into kilojoules?
Oh, sorry.
So is it joule?
I just started doing kilojoules out of habit. They're all joules. If I just gained a massive amount of energy, otherwise that'd be insane. Okay, where else did the energy go? Yes.
In the string of the bow, as well as the wood.
Yep.
itself.
Yep. Vibrating.
Sound.
Wait.
Ooh, sound.
Is it 90 joules or 90 kilojoules?
Joules.
No, no,
No,
no.
but
in the
above
green.
it says
Oh.
It's jewels, man.
So everything.
I
Yes, you actually did.
never wrote that.
Oh, yeah.
Yeah. We have sound. Sound is just kinetic energy. When I go like this, when I hit, that creates that just moves air particles. Those air particles then hit air particles next to it, which then hit air particles next to it, and they just keep doing that until they hit the actual drum inside your ear, which vibrates that. When that vibrates, it moves a bone, and that bone activates a nerve, and then you interpret that as sound. It's all mechanical energy, or kinetic energy all the way along. Yeah. Birdie, question?
Sorry, no, I'm talking. I just.
Question?
No, I
you
just-
just said something very stupid.
I didn't. Okay.
What? No, and we don't criticize people for that, especially not science class. Everything's a question. Timmy, do you have a question?
Not so far.
Okay. How many kilojoules did you just sound? One? Sure. It might actually be a little bit more than that. Sound could be fairly powerful.
It's not in kilojoules.
Keep putting it in kilojoules. Maybe I should have just started in kilojoules.
Yeah, maybe.
Yes.
What about like wavelengths and like frequencies?
Yeah. What about them?
Is that also like mechanical?
Yeah. Well, in terms of sound wave, yes. When you see a wave moving, right, in the ocean, it's a wave,
Yeah.
right? But it's physically particles moving up and down. That's kinetic energy. So same with sound. There is a oscillation in the air that's moving across that pushes air, so it gives the next one kinetic energy. It's a wave in terms of you can measure it and you can see them moving and it gives a wave function. But it's still just kinetic motion. Yep.
What about the wind?
The wind. Where, in what way?
Where you like rest, like subtract joules from the air.
So the wind going like
Yeah.
here.
Especially
So
if it's going 200 miles an hour.
I'm going to represent it like that. Wind. So like air resistance.
Yeah.
Air resistance. So it is physically hitting molecules of air and bouncing them out of the way. What kind of energy is that?
Kinetic.
It is kinetic fundamentally, but what property of the air is being changed?
Boom.
Let's say you did that 1,000 times in the same spot. Would the air get hotter or colder? Hotter. You're moving air. Have you seen the old YouTube video where a guy tries to like cook a chicken by slapping it?
Yeah.
Yeah, they did that.
Yeah, slap. They never did that. His conclusions
Did it
were
cook?
insane.
No,
Did it work?
But the one, no,
No.
they wrapped it in tinfoil, and then they set up it to like a motor and it took like 20 hours.
Yeah, and he managed to show he raised it by some small degrees and then extrapolated that eventually they could cook the chicken. No, because the heat is also escaping while you're hitting it. It will never reach a temperature ready to cook it. You're just going to get a very mushy chicken eventually that will slowly decay while you're hitting it. It's terrible. But it illustrated a really good point, which is heat is just molecules moving. So in this wind resistance, you're just heating up the air. So this is actually a form of heat. All of the waste energy is usually kinetic. Kinetic eventually devolves into heat. When the sound is moving the air particles and it hits things, it eventually just dissipates in your heat. And you can find that right away, because as you know, if you take your hands, everybody take your hands. And then you rub them. And you can actually make it really hot, because you're just turning all the heat. Timmy had a question.
I did.
No, Ben had a question. Or was it Birdie had a question? Somebody over there had their hand up.
What was it?
It was Ben. Okay.
Oh yeah. But if you put it in like a vacuum with no heat and just kept slapping it.
Oh, if you put it in a vacuum, you have now made it very difficult for the heat to escape. Not impossible. In a vacuum, heat still escapes via infrared radiation.
But would that
And so it would still lose a bit, but it'd be very well insulated. So it might retain a bit more. Again, the speed at which he could heat it up, I still don't think he'd get it to the point that it would cook. But a vacuum chamber would have a much, much better chance. I still wouldn't eat it, because even if he did cook it, I think it would take days, and the chicken might have botulism by then. But maybe. Yes?
Would it work in a closed system?
A closed system just means the heat doesn't escape the container, and what you want is for the bird to be a closed system, not just the container, because the heat's escaping off the bird. But if you made a small enclosed system, then essentially you've made a fancy oven in which you're heating it up by slapping the bird. So if no heat escapes at all, and it just slowly the whole container heats up, that would be much better. Yeah.
You said that like sound, when you make a sound, it'll eventually dissipate the heat as well.
Yeah, because that's just molecules
not
moving.
Then just, get a really loud speaker or really fast moving one and heat something up.
Yeah.
Is that how microwaves work?
No, microwaves work by literally moving molecules. So microwave beams are just large enough to not break but oscillate a molecule, and when a molecule moves, it generates heat. It primarily works, the microwaves are tuned at a length that primarily makes water and fat heat up, and then that heats up everything else. Okay, I think that's good on that page. Anything else? Oh, I got stuff on the bottom. So, we've got lots of forms of potential energy. I will write potential energy. Oh. There are actually 3 ways to abbreviate this. I think your textbook and I will often use potential energy. And then there's energy of potential. And then there's energy of potential where you make the P small to show that this is energy of potential. All of those formats are used. Hands, if you have a question. Yes?
Doesn't the arrow still have potential energy because it now it's moving at speed?
Until it's all kinetic, yeah. Because as it's going, it's converting that potential into kinetic.
Yeah.
At least until it hits the ground. Yeah. What is the SI unit of potential energy? Joules. Thank you very much. What is a joule? Yes? But it's a fancy unit. It's not a real unit. It's a unit made of fundamental units, yeah? In order for you to derive that, I might as well just give you the formula. We haven't done it yet. I think no, we'll derive it later. The shorthand for joule is J, and we'll derive this. A joule is equal to a kilogram meter squared per second squared. So if you ever are working on a formula, like you forget the formula for something, you're like, how do I get that? Well, if you can multiply and divide the units, so you get a kilogram meter squared per second squared, you've gotten energy. So whatever you're calculating, you would know, oh, this is a form of energy. So a joule is just a shorthand for that. Good? Anybody still need to write it down? Timmy, question?
I don't know.
You seem to be glaring in a way. All good? Okay. Acceleration of gravity. How fast do things move on Earth?
9.8 meters.
Hold it.
Wasn't it that like?
This is in the wrong spot.
Yeah.
That's pretty fast.
Hold it. You don't have this one next.
No, I'm
You got that one.
Yeah, I'm here. Exist. There we go. Apologies. Wrong page. What is the resistance to a change in velocity? Whoa. 1 second.
Drag.
velocity. This.
Thank you for volunteering then. Come. This is very similar to another demo we did. It's the same one actually we did earlier in chemistry.
I have
Yeah.
a question.
Yeah, you volunteered. Excellent. I'm going to stand here. No, right there. Okay. And then what I want you to do, go like this. No, like this, like football player. You're going to hit me.
I don't play football.
Okay? So you don't have to play football.
He's going to.
This
You
is
lie. You play football.
No, I
You
play
just,
center.
we just call it soccer. Ah. So what I want you to do is I want you to run into me like this.
That's actual
Okay?
football. That's real football.
Okay? Run into me. Okay? I'm going to move slowly along. I want to run into my heart. Okay? Go. Excellent. Hand. Thank you. Number one. Who bounced? Right. Because I have more inertia. Huh?
Yeah, but if she doesn't have speed,
No, hand is a good question.
then
Yes?
but it could mean that you still bounce if she has enough speed going the opposite.
Enough speed. In fact, speed is more important than mass, but we were both moving kind of slow. My mass is fairly large. An object in motion, finish the sentence.
We'll stay,
We'll stay in motion.
Will stay in motion. Ooh. Will
Wait, that's not.
stay
Is that
Motion
in motion
I'm gonna say.
unless, what'd you say?
acted
Unless
upon.
it's disturbed.
Unless disturbed.
Got it.
And some of you may have learned this as an object at rest will stay at rest unless
Yeah,
disturbed.
that's what I was.
Yeah.
They're exactly the same thing because something that's moving is not moving if you just consider everything else moving around it. Your point of reference is always relative to everything else. Okay,
I have a question.
question.
Did you hear the manhole how they got like launched into the stratosphere?
Vaguely, yeah,
Like,
yeah. From a
How did
nuclear
that
explosion?
Yeah.
oh, there was
Yeah.
an explosion.
Yeah.
And then it just like
explosions
Yeah,
that happen
yeah.
here is all of them.
Yeah.
No, I know
Anyway,
there's I was
here,
just
back one.
Can I touch
Excellent.
no.
Actually, no.
How it happened.
No, I want you one closer.
The
There.
pressure from the explosion.
Yeah, perfect.
I'm wondering if you knew what happened.
Zane,
Wait,
what is a change? Yes.
Yeah.
Zane, what's a change in velocity?
It's like speed.
Velocity is approximately speed. So if I say I have a particular velocity, that means I'm moving with a particular speed. But velocity actually has one thing extra that speed doesn't. Speed is just like meters per second, kilometers per hour, miles per...
Does velocity have
Whatever.
height?
Velocity has something like height. It has speed and direction. So a change in velocity, what do you call it? You're going along in the car, and then you see, oh my God, the light turned yellow, and what do you do then?
Decelerating.
Some of you put on the brakes, some of you hit the
Gas.
accelerator.
Yeah, the gas.
So you hit the gas and you just feel that whoa because you have this amazing vehicle. What are you doing? Accelerating. What are you doing if you hit the brake?
Decelerating.
Decelerating. What do you feel inside the car?
You go backwards.
Yeah, you feel the force. You get pressed backwards. You press forward.
G-force.
Oh, this is an interesting one. If you ever have helium balloons, put them in your car. Okay, and when you hit the brakes, when you are driving, you all have your licenses, right?
Yeah.
Yeah, okay. When you hit the brakes, which way will the balloon go?
The opposite. They'll go backwards as you go
Forward.
Or-
You'll go
We'll
forward,
go forward.
and the balloon will go backwards.
What?
Why does the balloon go backwards? No, hands, and your hands first.
Because like they're lighter. Get out of the way.
Because the air around it's denser, so the air is going to go forward. Well, it goes backwards. The most dense thing is going to go forward.
All the dense stuff's going to go forward. Think of your vehicle being filled with a bunch of lead marbles, and the balloon. The reason it's floating is because it's so much lighter. It's full of like little plastic marbles. When you hit the brakes, all the lead marbles go to the front, and the balloon then gets shoved to the back. So all the air gets pressed to the front when you brake. So all that mass moves with you. it used to be very dangerous for trucks early. When would this have been? Like the early 60s? So imagine a milk truck. It's hauling a big, huge container of milk. This could be also be gasoline, any liquid. It sees a stop sign that it didn't see before, and they hit the brakes. Truck stops. But all that liquid that was in the trailer's not all the way full. It's just 3/4 full. So what happens to the liquid when you hit the brakes?
Sloshes back.
It slushes, yeah. And it will start a wave. And then that wave will come up because it's heavier than the air inside and hit the front of the trailer. And then the whole truck will just jump 50 feet because there's a lot of energy in that. They now put baffling in there, so even if you create a wave, it's a bunch of little waves, not one big giant one. There's less jostling, and they tend to have more regulations about you got to fill it all the way to the top to prevent that from happening. But it is amazing to see when you see it. I've seen it once. They stop, and then the truck just seemed to like just spontaneously jump because the wave takes time to travel. So, a change of velocity is acceleration. And you can say, if you hit the brakes, it's deceleration, but it's the same thing. We just call it deceleration negative acceleration. It's all acceleration.
How can you accelerate?
Units of acceleration.
Meters divided by 70 squared.
Meters per second squared. Well, what are the units of velocity? Meters per second. So we don't tend to use kilometers per hour. If we're driving, sure, it makes sense because, well, we can go this many kilometers an hour. But we're measuring in physics, we measure in meters per second. Those are the SI units. And then if we want to measure how fast are we increasing our velocity, then we're measuring in meters per second every second. So it's meters per second per second. So that becomes meters per second squared. And that is when you have a change in your velocity. Now you can change your speed, but what else can you change to have an acceleration?
Can you explain that again?
If you are moving at a certain velocity, so say 10 meters per second, and let's say you're going here, meters per second, that's times 0. You measure it's a car. I'll make it an arrow actually. It's going 10 meters per second. 1 second later, it's going 20 meters per second. 2 seconds later, it's going 30 meters per second. How fast is its speed increasing? 10. So it's increasing by 10 meters per second. So that is meters per second squared. Okay? So that's why it's acceleration. Now, in that I changed the speed. What else can you change for acceleration? Because it's not just speed, it's also direction. And you can see that in all sorts of ways. If you're going around a corner really fast,
Slow down.
you should slow down, but if you don't,
You drift.
You go.
let's pretend you're on rails then. What happens to you inside the car?
You go to
You go. And an object at rest tends to stay at rest. When the car is turning, your body's trying to keep going straight, and so that is what's keeping you like that. Now, weirdly, if you're in a turn and you realize maybe you're going a little too fast, there's a little too much, maybe you'll flip the car. Do you slow down or speed up? You speed up. If you speed up, you'll actually make the force go inward more, and you might make the turn. Don't get in a car accident and say, Mr. Neufeld told you to. Have some driving lessons first. Now, where's this? You can see all sorts of effects of things like this. Because if you're traveling at a particular speed, you know, I have speed, and if I got faster and faster. But if you just want to continuously accelerate, all you have to do is spin, because I'm constantly changing my direction. I'm constantly accelerating. And then weird things can happen, because if I'm spinning, watch what I'm going to try and spin. I have a terrible sense of balance, so this may or may not work. But I'm going to spin, and I'm going to try and pull my body in. See what happens to the speed of my spinning. Okay, so I'm going like this. Oh, don't fall off, Mr. Newfoundland. My legs are too long. Okay, go round, 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 round. Pull it! Ah! What happened to the speed? Increase. Get on your chairs, create a little bit of room, probably one of you at a time, because I can do that. But put your arms out and then pull them in. Oh, I could have put them in and then pushed them out.
That's mine.
You don't have any space.
You know how to spin on like.
And then out and then pull in.
You know how to spin on skates, right?
Watch out, watch out.
Okay, don't wreck the thing.
That's insane. Wait, you know, like,
Well, Zane, we're not no crashing derbies.
No, it's the same thing. Stick your arms out.
Stick your arms out and then pull them in.
if only I had space to do so.
Or have them in and then push them out. Okay, you guys can spin it. Let pull back. Give them some room.
Like, so spin around, stick your arms out.
Okay.
You don't know how to spin on skates.
You don't know how to spin on the chair.
My chair's too high up.
Oh yeah, you should probably not do that. So don't do that.
Okay, I'll do it.
Everybody felt a spin. What happens when you pull things in?
Keep your arms towards that way.
Out. Don't get slower. Yeah. So
Alright, spin jig. Nah, we gotta hit it with the spin jig.
Oh no!
Oh no!
You slow down and push your car out. But if you speed up,
Kieran, move out of the way. Let me show you this.
Oh, I'm gonna have
you
to.
should slow down before when you slow and then speed up, not really quick.
That's fast.
Okay, back to your desks.
What's on?
That was what? Oh, phone.
Skates are different from watching on.
No, I've done skating like very few times. I don't like it.
Where'd it go?
I end up going too fast and falling.
Where did it go?
No,
I can skate backwards, but I
I
can't
can do like 6 minutes
I can jump spin, but I can't do the twist. Yeah, I can.
What? You can land it?
Yeah.
I want to learn how to
That's
backflip skates, but like,
it's not too hard. It's
I
just
lost
a
one
jumping.
doing that.
Big jump.
it's illegal actually in skating.
Yeah, because you like,
It's done. It's done.
Yeah,
I
it's
think they should
dumb.
allow
because the whole time I tried to test it, but Alicia was just jacked.
So while it like
Oh, I loved it. I loved it so
you jump
much.
this game.
My husband-
And so then it's like
hurt yourself easier.
I like skating.
Well, I like it.
I can imagine breaking.
I find that like it's actually like a safer.
Safer for other people because it's less of a
Yeah, well, less than
Yeah, no,
they
they
don't
don't
need to worry about something. Especially if you're like
I'm pretty sure
yeah.
Okay, so your attention.
Bad as hell, 'cause I can't kick
Medic. This is not going to be a hard thing right now, just in terms of, this is a very sort of what happens when you are in Earth's gravity. So, although I zipped you around, we're not going to go outside and go to things. So I'm going to take the little skateboarder. What happens when you go down to the velocity? And what happens when you go up?
speed up, down.
I don't know if I made that curve quite smooth enough, so this also might be a little bad. Go. That's not a realistic skater.
How did they manage to make it to the sun?
In that half second, he pulled like
And
24
like,
Gs.
theoretically,
Can you do a loop?
What a beast.
Okay, I need to make a better one.
do it loose.
I'm-
Yeah. A jump, good jump.
No, I'm just going to do a very simple,
yeah, very simple.
very simple.
Wait, can you make the dog?
The dog?
Yeah, it's dog.
Oh yeah.
He's not being.
Oh, yeah.
Wait, you don't have to-
No,
Yeah,
that one's got it.
Okay, and when you go down, what happens to the velocity?
Increases.
And when you go up?
Goes
Ah, Oh, look, the dog even turns around. We can increase the force of gravity. Whoa! And
Increase the force of gravity.
you can decrease the force of gravity.
Wait,
But there's
shouldn't if you just like launched off there because he had all the speed, then you decreased it?
Yeah, the answer to that would be yes.
You just kept going.
By the way, it starts at Earth's gravity, and then you can go all the way up
What
to
if
26.
Like, if you like,
You go down.
as he was falling off, you really increase. Like, can you increase gravity right after he falls off?
Increase my
Oh, well, yeah, we can increase the mass. So at the top, I'll increase the mass. So now he has
And what do you
a
get? So bottom,
huge
you
amount of
increase
more mass, and then no mass.
Yeah.
I don't know that made a huge
Yeah.
amount of difference. Yeah.
No. Increase gravity
Yeah.
on the way down, and then
then
decrease it.
decrease.
Oh, not fast enough.
I just wanna see him go off and then.
no.
Whoa.
We also have no friction. So,
Kill the dog.
killed the dog. He was a good dog. No, he wasn't.
Oh, there's a cat.
Can we make a jump?
Cat. Okay.
Oh, we have to kill him.
And
Yeah, we have to kill him 9 times.
in the end, what form of energy does friction generate?
Well, heat.
Kinetic with heat. There might be some sound, which eventually goes to heat. So speed increases, decreases. But right now,
Shaz is real.
with no friction, how long will this happen?
Forever.
Forever. But I can increase the friction, and then what will happen? Eventually stop, because it's just slowly converting to heat, and the poor ride will not work as well for the little kitty cat.
Can you turn the friction all the way up?
All the way to there? Yeah, now it's like
Why didn't it
nails.
just stop?
That's just like really bad wheels.
It should catch fire if the friction is so high.
Stick to track. Ooh! Oh! It's on stick to track.
Oh.
Oh, no.
No.
Wait, now you can kill the cat. Kill the cat.
Oh.
Do a flip.
I think it actually got to do with it.
No flip.
Do a flip. Kill
Or
the
you
cat.
make, can you make it do a jump?
Yeah, can you do like directional energy as well so that it'll do like the flip, right?
No, I don't want that. Wait a minute.
You don't like cats? Yeah, I don't like
Kill the cat.
Can I put like SpongeBob on
cats.
Okay.
Let's see. Whoa.
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 Oh,
But lost it all because it hit that, and then I like I was just doing that. Okay, that wasn't supposed to be. Climbs up, increases. Hold it. No. Decreases.
What it is.
Tries when it rides down, its velocity increases. Timmy, Birdie. When it coasts, its velocity is Birdie. Say, Birdie. When it coasts, its velocity is. When it coasts. Do I need it back?
Interval.
Constant.
Yeah, when you're coasting, what if you had no friction, you're just coasting.
It's like it's off.
What would your velocity be?
Constant.
Constant. You're not gonna, is it going to change? No. So it's just constant. If you fire, so if you're in space where there's much less friction than down here on the planet, where we have lots of air molecules in the way, you fire something off, it's going to go forever until it hits something. So we've put out spacecraft. There's a spacecraft that's exiting our solar system as we speak that was launched in the 60s. Lots of weird stuff was happening to it for a while. It turns out one of its instruments are down. We actually managed to fix it. It's still taking readings. It's still giving it back to us. But when we lose control of it, it's still going to keep going. It will be going for millions and millions of years. It probably won't decay that much because most of the decay that would happen would be here in our solar system. Because even though there's not air friction out there, there's lots of solar wind and radiation from the sun. But it is now very far away. It is cold and it is dark and there's not much there. And it's going to be in stasis like that as it drifts forever. Remember,
How can you
Did they
fix
manage
as your parents tell you, always reach for the stars, because even if you miss, you'll end up without air or water, endlessly drifting in space. Yes.
How can you fix something from space?
So when they fixed it, they didn't go to it, but they do have communication with it. So what they end up doing a lot of times is they reprogram it.
Oh.
So one of the chips malfunctioned, so they reprogrammed it to reroute all instructions around that chip, and now it's back to functioning again. It can still work. Yeah. And our programming techniques also got better over time. It's had like software updates. Now it takes a really long time, and this computer was built in the 60s, so it's not good. Like it doesn't have a lot of memory. Bill Gates is famous for saying that your computer, for its memory, probably doesn't need anything more than 512 kilobytes. We regularly now put gigabytes in our computers. There was a time in which we thought you didn't need that much. But computers evolved quickly. What is the... Zane?
Yeah.
What is the value of the acceleration of the velocity is constant? See here? 0. 0 meters per second per second.
Infinite. No, 0.
Because if you're going 50 meters per second, and then in the next second you're going 50 meters per second, how much did your speed increase by? 0. So the acceleration is 0. You're not accelerating, you're just coasting. If you're driving a car, if you're staying at the same speed, the only thing you're using up gas to do, or diesel, depending on your car, or electric. If it's electric in this province, you're getting it from hydroelectric dams. Ariel, Zoe, separate it by desk, please. Ariel, please move one over. No, actually. Yes, move one over. Zoe, switch places with see here.
Oh.
Excellent. Excellent. See here, what you're supposed to say is yes. Yeah, there you go. Oh, this was because I didn't used to have that cool little FET thing. So let's label that. Do we need to label that? Probably. So you have a reference. So, here, velocity is fill in the blank.
Are you putting number?
Acceleration is two V equals A equals 3 V equals A equals.
Are we putting numbers?
Nope, I just want, so increasing, decreasing, positive, negative are all words that you can use. You don't have to give me actual numbers. You could give me a number if you know for certain. It's like the last one, it's 0. But I haven't told you any numbers. And this is going to take up a lot of room. So rather than saying that making this say velocity is and acceleration, I'm going to do what I did over there, which is just to make it V equals and A equals. V, oop, wrong color. One, V equals A equals. Okay, fill them in. While you're doing that, I'm going to do attendance, and I'm going to ask someone at random to fill them in. So attendance. Well, that was a panic for a second. Science 10. Attendance. Alejandra, Ariel, Ben, Bertie, Felix, Hugo, Jonathan, Kieran, Kieran Zane. Not loud talking in the middle. Whisper talking. Lisa, Matthew, Naomi, Takir, Kimmy, William K. is not here. William Wren, Zane, and Zoe. Has anybody seen William? William, who normally sits over there?
Oh, no.
No? Okay. Okay, first up, Ariel. What is the velocity doing at point number 1?
It's going up.
It's getting faster?
No. It's low.
It's going slow, so it's decreasing. Let's get the right color. If it's going this way, and that should be clear too, it's going that way. So what is happening to the acceleration, Alejandro? Is it slowing down or speeding up? So it's getting faster, is it going that way? Slowing down. So what would that mean for the acceleration? Acceleration positive or negative? Negative. Do green. Felix, what's the velocity here?
He went to the bathroom.
Oh, curses. I'll get him as soon as he gets back. Timmy,
Yes.
velocity here, what's it doing? Increasing or decreasing? Pardon?
Increase.
Increasing, going downhill. And what is happening to the acceleration, Bertie?
Increase. What's that?
Also increasing, yeah. Well, actually, hold it. I don't know if that's increasing. Is the acceleration positive or negative? Positive. Yeah, it's positive, but there is a quantity known as the acceleration of acceleration. So if you're accelerating, like let's say you're going 10 meters per second, and then a second later you're going 20 meters per second. What's your acceleration? 10 meters per second. But let's imagine that in the next second you were going 40 meters per second. And then in the next second, you're going 80 meters per second. Your acceleration isn't just 10 meters per second. You are increasing your acceleration every single time. And so you now have an acceleration of acceleration. They actually have instruments that measure those when they fire up rockets because they're accelerating so quickly, their acceleration is accelerating. That's a lot of force. Zane, velocity for 3.
Is it constant?
Yeah, it is constant. Well done.
Because we're not taking friction into account.
We're not taking friction into account, just like the poor skateboarder. A lot of times in our physics, we're going to ignore friction, except when we don't. Lisa, what's the acceleration? 0. 0 meters per second squared. Excellent. So, what is the formula for acceleration? Anybody know? Did you do this like in grade 7, I think it was? Yes?
No. Is it current speed minus initial speed over time?
Yeah. Over time in that way. Acceleration is equal to the change in velocity over the change in time. So when you see change in, that is equal to the final minus the initial. It doesn't matter what the quantity is. Does anybody know what that symbol is called? The triangle?
Delta.
It is change. It's a delta. In physics, we borrowed the delta to mean change. You'll occasionally see a symbol like this. That's a little delta, like a lowercase delta, and it means a little change. You'll see that in Chem 11 if we ever do that. But that's the only one you need to know. What I would like you to do, solving any problem, is 1. Ben, Bertie, identify the problem. Put in the correct formula. Calculate algebra state answer. You must write the formula without numbers in it. So write out the full formula. So write out A equals VF minus VI over TF minus TI, and then substitute your numbers. Do not use an equal sign to mean next step, like put another line below and show what you're calculating. In addition, I've noticed one of the key difficulties students have is nothing to do with their math, but that they lack confidence. They stop right here, because either they don't know what to do, and they go, well, I'll do nothing then. At which point, make a guess. Use a formula. You see things in there with speed, just any formula with speed. Do something. You might be right. It is amazing the number of times while doing that you'll get on the right track, or you'll have done something correct even if you come to the wrong answer. Or you see, because word problems can have lots of possibilities, you see 3 separate ways to do the problem. You're not sure which one is right, so you do none of them. You don't have the confidence to pick. Confident people pick a solution and then get it wrong, and then get 4 out of 5 marks because they got most of their actual calculations correct. They just picked the wrong approach, or they did the actual math wrong, but the method is right. As long as you show something at this stage, what you're doing is more important than the right answer. That'll be true for a very long time.
I got a question. Because it's acceleration, so it's different in speed,
Mhm.
right? So then what happens if, let's say you're moving 14 meters per second in one direction, right? And then all of a sudden now you're going the opposite direction at 56 meters a second. Would you say your acceleration is 70 meters a second? Or would you say that it's only...
Hold it, no. You were going this way, and then you turned around.
And now, yeah, and then you're going the
So
opposite
your
direction.
acceleration is now negative
Okay.
in
so
the other
it's-
direction. So all of these have direction. If you change
So-
direction, you've changed it.
So then there's 2 options, but what happens if you turn around and go at an angle? Then is it still at the perfect negative?
Every time you change direction, you're doing an acceleration.
Okay, so then it's...
So that would be a new type. We're not going to go that complicated, because that is physics 11. They'll do changes in direction and the forces involved.
Because, like,
We're going to do straight line travel.
This direction, but then...
No, I want you to
that
stop.
direction.
No, not it.
Exact
Because we're not doing that, I want to go on to the next piece so that we can all practice. Because I want everybody to grab a pen, because I want to see all your calculations, and I want it to come around on a piece of papers. This is not in partners, because I want to see yours. I want you to identify the problem. Ooh, I'm going to plug this in. Write down the formula, put in the numbers, calculate the answers, and sign it underneath. I want to see it on the board so I can see what your workflow is, and that you know how to do math problems and how you set up. Yes?
What does it say?
What? Identify, formula, calculate with algebra, and then state your answer. I'll rewrite it in text, but grab a pen, pick a spot on the board. Why is this not plugged in? Oh, it wasn't turned on. There we go. But yeah, if you're changing direction,
Yeah, because then it couldn't be, because if I'm going this way, then I'd go this way, then is it just the amount and I'm still going this way? Because I'm changing the angle which I'm doing.
Yeah.
Am I measuring the speed I'm going this way, or am I measuring the speed I'm going this
those
way?
are two different
Because
vectors.
now, if I go like this, I'm
No,
still
no,
going this way.
those are two different vectors, and there's a way to take like the average of them in terms of where your force is at.
So for this answer, it's anywhere from
Nope,
minus
because I didn't
70
change
to plus
direct. I
40.
didn't change direction.
Yeah,
I
but
was
doesn't
traveling at that
state
speed.
that it doesn't.
2 seconds later, I was traveling that one, linear direction.
It doesn't state that it is.
If I didn't state that a meteor didn't hit me, a meteor still didn't hit me. I would have to state a corner because that would change the problem. Yeah, haha. Gotcha.
Where'd it go? My drawing. Yeah, this is what he does. Oh, woo!
Grab a pen, find a spot on the board, write it out, and show your answer. I want to see your work.
Ain't it 21?
Pardon?
Isn't it 21?
Sorry?
Isn't the answer 21?
No, I want to see your work. I don't care what the answer is. As I was just saying in class, the answer doesn't matter. It's I want to see how you put out your work.
Where do you put the thing? Up or down? No, that's the sun. That's what is the best?
Wait, that's mine.
That's the that's
We have to do different words.
Let's go.
What's the F and the I for?
Wait, can I just click on here?
Then would that just be time?
Final and initial.
So it's just 2 minus
Oh, 2 seconds.
minus 0.
Okay.
Okay, I'm gonna come around. Show me your work. Now, at the end, what is state unknown?
I don't know.
What do you do at the end of a math word problem? Maybe you don't push this anymore. Right?
Data solution.
State your solution. So, if I said, what was his acceleration? You say, his acceleration was, or Mr. Newville's acceleration was, or you write, the acceleration is, and you put a little box around it. You have to state it with units. Okay. Call me over as soon as you feel that you are done.
Yeah. No.
Okay, can I
Word 42.
And I have to do it in
Oh, wait, no, but that's a math thing, and you wrote words.
You're talking
Meters per second.
Yeah.
Wait. Yeah, it's square.
Is it 14 minus 6? Yeah, no, stop separating. So, if you, like, because you did about half of that in your head, which is problem, and understandable. But what I want you to do is write out the full formula, put the words things in, that trains you to do that. You have skipped ahead to the part where you have to do minus it. So 2 minus 0 on the bottom. No units are in there. That's just a random calculation on the side. Sorry. Now, that is, yes, that is perfect. Will you read the other hand? Yeah, that's much better. Times 2 seconds. Units in the acceleration, 42 watt divided by what? Yep. And then where's your units for acceleration? Excellent. Now, yeah, that's good, but you need your units all the way. Acceleration is velocity is not. But the reason I'm saying is now that I've helped you, go find someone else and give them all the same everything. You were further strong. Sure. Where's yours? Why are you sitting back there? Oh, right. He's going to go for the board. I should see yours next. Oh, same thing. Were you listening over here?
Bro!
This is set up really well. You're missing all those things. Put your steps in and then you go. Okay, you can help. Zero. No, that's the speed which you, that's the time which you start to measure. 0 seconds. Well, when you start running, you start running from 1 kilometer to 0 kilometer. You start measuring time, you start from 0 to 100.
Yeah.
No, we can't. We're gonna make sure we get together.
But you travel 2 seconds. 2 seconds later.
Yeah, but this is initial.
That's a really good. Look at that.
Initial is 0. So I like you use all your units here, here, there, and there, but you need your units there and there. You need units here as well. Okay. So same, you need units. You have the units. You see? So you have 56 meters per second. What's 14? What are the units? Meters per second.
Bro, the fact that it says we saw a fuzz means that's enough that light.
Excellent. And you got 2 seconds. 42 watt over 2 watt.
Because like if it's a fuzz, that means like
Per second light. Okay, with all your units all the way through. And 42 slow out, that's just slowing down. Every step right there.
No, his acceleration within
Excellent.
and then he slowed.
Stay next to your work until I come around and see you. Joey, carry on. Okay, here. number one, you're missing your units. I need units for every step. For the seconds, it should be seconds. What are the units? That's right. That's correct. What are the units? What are the units of these two? Meters per second, seconds. And what are the units of 42 then?
Hearing your handwriting is
Meters per second, put them in.
I feel like he's only doing it to no.
Statements, okay, very similar. I'm glad I did this. You need units for every one of them. Every single one. Units of every single one. Zoe, where's yours? Show me.
You need units.
Ah, you already discovered it, yes. Put units in. Put units in. Oh, sure you can. That's like both up together. Yeah. Okay. Now we seem to be cooking with fire. Well done.
Just like go first, and then just quit.
I know.
Go. Dude, I'm gonna hit him like all the way. In conclusion,
That's his fault. That's his fault.
I'll hit him with all my force, and they'll just like stand there, iron clap. You know, you join us.
Okay. Zane, turn around, please. Focus on physics. Stay here. What are you doing?
We're talking about the velocity of slap bars.
Fair.
We're talking about like
Okay.
the rate.
Maddie? Not just folks.
To be fair, I was playing with. That was very fluid.
For this guy.
Like the slap one, we jumped.
What class was it for?
Spanish.
Even worse. Okay. I went around, did well, did it quickly. Most of you set it up correctly. I think part of it might be math teachers don't care about units. Do you math teachers care about units? No, okay.
Only for the
I heard the no. You need to care about units. Units.
Wow.
1,000 push-ups. No. Units matter because they tell you what's going on. They're often more important than the actual number. We want to see them at every step because they save you from getting mistakes. But also they tell you what kind of quantity you're dealing with. You can only minus and add numbers if they have the same unit. So if you put numbers in here and you accidentally put in the wrong one, if they don't have the same unit, you know you can't minus them. The units also tell you what your final quantity was going to be. If you took a velocity and you divide it by time, you get meters per second, which is meters per second squared. Because if you have, I'm assuming you have this algebra, but if you have 1 over a divided by a, what do you get? 1 over a squared. So you can derive your units. What were the units for the original joule?
J.
Yes? What were the fundamental units?
Kilogram.
Kilogram?
Meters squared.
Meters squared per second squared. This is not a kilogram meters squared per second squared, but it does have meters per second squared, which means if you added a mass, kilogram, if you added a mass and you added a kilogram and you added a distance, so a mass with distance and an acceleration, you now have joules.
Yeah, but don't.
That tells you where energy comes from. You can just now make up formulas because as long as you get to the right unit, that is what energy is.
Nice.
It is a kilogram meter squared per second squared. So you want to keep track of those. And you'll thank me later because at some point we stop giving you formulas and you just derive it with the units. You know you have to get meters per second. Why do you need distance over time? It's just meters over seconds. Okay, mass and gravity. Mass and weight are different in physics. I know they're not different in terms of common parlance. Hold it. Did I finish off the other page? Is there anything else I needed to do? I didn't have a question underneath it, did I? No, I did not. Excellent.
Who invented the test?
Mass.
of things underwater as well as air?
Mass is measured in kilograms. Weight is a force measured in newtons. On planet Earth, if your scales do that conversion automatically, so we consider weight and mass to be much the same thing if you're measuring in a kitchen scale or whatever. However, in physics, we want to be very specific because if you are floating in space and you're absent any gravitational force, did your mass go away? No, you still have the same mass. You're just not being accelerated towards a planet. You don't have that force pulling you down to the ground. But what has changed is your weight. So your weight is different on Earth, on the moon, in space, on Mars, on a very, very large asteroid. But your kilograms are going to change. Objects with mass. Are attracted by a force. And the weird part is everything attracted by a force. Attracted. Attracted.
Whoa.
Larger the mass. Larger the mass. What happens to that force? Greater the force. All of you have mass. All of you have a gravitational attraction. You are gravitationally attracting everybody right now. And in fact, the force of gravity does not disappear. You are theoretically, well, not theoretically, in actuality, you are attracted to every single mass in the universe. It's just that it spreads out, so it gets weaker over distance, but it never quite goes away. Which is why we can do things like gravitational lens, gravitational surveys, and see what's out there.
If we're all getting pulled together, does that mean eventually we're all just going to clump off?
It depends on the amount of force. So it is literally in everything around with everyone, which has always reminded me of this quote, which I will quickly now shut off the live stream because this will get me copyright banned because they're litigious jerks. So let's turn off that.
as gravity goes farther out, its strength is going to get weaker and weaker.
Yeah.
As it goes farther in, it's going to get infinite
Stronger and stronger. Yeah.
Like to an infinite point, and that's what causes black
Well,
hole. Or is
but
it
remember,
not?
it's not an infinite point because you don't have a point. You have a planet.
Right.
So as soon as you hit the surface of the planet, if you go below the surface, you now have mass above you as well as below you. So if you manage to make the center of the planet, what gravity would you feel?
Well, everything around.
Around you. So it would all cancel out. You'd feel exactly nothing. You'd float in the center of the planet.
But you get crushed.
No, well, if you made a little, like, somehow managed to keep whatever, core is there. If you made a little hollow section, theoretically, you could just float there.
Got it.
Yeah.
I was thinking about going to coding tutorial real quick.
Okay. I gotta run back to the house.
What do you mean Python tutorial? Yes, this is his final project.
Hold on.
How's yours?
It's supposed to be one.
Well, we're supposed to keep it back. Thank you, Mr. Phil.
You're welcome.
Have a good day.
the end when I hand it out, you can just go early. Does that work?
Yeah. I behind every single one of my classes.
You-
My migraines are just still going. So
Ow.
they're not really taking the hint that I need to just do what I need to do.
Sorry.
The only class I'm not falling behind in right now is biology. Because biology, I could not pay attention the entire time. I don't. And then I can study before the test, and I can understand it, and